Ken.
Hey, how are you doing?
Good. Yeah. Okay. Oh yeah, I think I should have addressed that. You sent me an email about Lagrange multipliers.
Yeah, I think I kind of figured it out, but it was just a little like hiccup I didn't really understand. Yeah, it was just like
it's hard to answer these questions on email, so I was just delaying it. Yeah.
Right. Yeah, it had a lambda, and then in parentheses it had the constraint. You know, the r vector dot r vector minus something, right?
Mm-hmm.
And then I think it was I don't know. I think it was supposed to have a half in front or something because like when you do the derivative, you know, it's 2 lambda r.
Yeah, I sort of read through your email, and it seems like there is a typo in my notes, but I haven't carefully looked into it. I don't see anything else. It seems like there is a typo, yeah. But I wanted to look into it more closely before I reply, and I never got a chance.
Yeah. I mean, it was really. I mean, really, it's no big deal. But,
yeah.
Mainly now, a lot of my. Sorry, I was going to say like mainly now a lot of my questions have to do with the D'Alembert principle.
Yes, D'Alembert's principle. Yeah.
Yeah. The connection between that and Lagrangian multipliers, I haven't really made.
It is mostly conceptual there, and I would say read about it. The basic idea is that Lagrange multipliers tries to take care of the constraints. Like in Newtonian physics, we have the normal force, right? Normal force is there primarily to take care of the constraint that the mass is supposed to be on the surface. It cannot go inside of the surface or cannot fly off from the surface, right?
Mm-hmm.
So similarly, force of tension makes sure that the mass is at the tip of the string. It is not going to relax, right? Or what do you say? It has to be tight. Right? So those are constraints, and the way it is done in Newtonian physics is force of tension and force of normal force, and it comes reasonably intuitively there. Here it is not obvious, so we try to see where are the normal forces and forces of tension, and we try to introduce it as a constraint. And the coefficient, apparently, it seems like usually has the information about the force. That's the sort of the idea. But we can talk about it, yeah. Try to read about it here and there and come back to me. Ask me again. Does that sound reasonable?
Okay. Yes, for sure.
Okay. We were doing Kepler motion, and we sort of got the solution, but now we want to analyze that solution. So just for homework, I think there is a homework due today. Which I'm covering only. Actually, yeah, the content of the homework doesn't matter. It can be done. There's due. And there'll be 2 more homeworks due every. That's when we will finish the semester 2 or 3 more homeworks, I think. Yeah. I haven't posted that yet, but soon. So if you're doing Lagrange multipliers, that will be homework 10, if I understand correct.
That, yeah, the Lagrangian multipliers, that's for like the midterm and stuff.
So that's a homework 10, correct? So you're pretty much caught up except for homework 11, right?
Yeah, and I'm gonna have that probably turned in Tuesday. So
Okay, sounds good. Good.
yeah, I have a quantum midterm Tuesday, so I just got a lot going on.
Yeah. As I said, feel free to be responsible about it. That's all. Okay, we were talking about solution being conic section. So let me call it conic solution, right? So it's think conic section as solution. Maybe. So as solution to Kepler problem, solution to Kepler. So what we are talking about is there are two masses, M1, M2. We started by saying there are two positions, which will be 3 plus 3, 6 coordinates. But we came down to the point that if this is the vector r, and if I choose this in a plane, like if I have all the velocities, everything in a plane, then they will remain in a plane. And that's because angular momentum is conserved. And then there is just this vector r in the two-dimensional plane. So that is polar coordinates of a plane. Cylindrical polar coordinates does the job. And we showed that the Lagrangian then is dependent only on r, phi, r dot, and phi dot. In fact, because angular momentum is conserved, even this comes out to be too much. So we can get rid of one of the coordinates again. So this is half mu r dot square, where mu is the reduced mass, 1 over m1 plus 1 over m2. And we are working with, it should be minus of the potential energy, but the potential energy for gravity is negative. So it's plus alpha over r. So that U, potential energy due to gravity, is minus alpha over r. Let me not introduce that U very explicitly here, because very soon I'm going to define an effective potential. So I don't want it to be confused. So this is the act, or let me call it, yes, just to clarify that this is not effective potential. I'll start introducing something called effective potential, which is different from this. We showed that our equations of motion is, first thing that comes out is that mu r square phi dot is equal to a constant, which we call as the angular momentum in the z direction. Or if we choose our angular momentum to be in the z direction, it is a total angular momentum which is chosen to be in the z direction. Here. What are the equation of motion? We said if I were to write, so this is a constant, correct? So maybe in constant. There's one more constant, which is the energy, which is again the kinetic energy here, mu r dot square plus half mu r dot square by phi dot square, but we like to write it as in terms of the angular momentum. So since there is a phi dot here, I can actually say this is 1 plus 1 by 2 LZ square over mu r square. So this is LZ square over 2 mu r square. Or I changed my mind. I'll write it as it is so that it's very clear where it is coming from. Sorry about that. So that's phi dot square and the potential energy, which is minus alpha over r. This whole thing is the energy E, which is equal to a constant also. Right, that's a basic idea, and it is nice to know that there are these two constants, and these two constants specify the orbit completely. And keep track of that. We will change the labels here a little bit, but mostly there will be these two constants showing up in some form or the other. And we showed that our radius as a function of, we should have it as a function of time, but then we said that time and angle are the same. As far as they're monotonic, there is a scale between them. It's not just a scale, it's a function. Like phi is a function of time, which is always monotonic. So why not use that as your time? And this is equal to a constant R naught divided by 1. Was it plus or minus? I don't remember. It came out to be plus, I think. Right? 1 plus E cosine of phi minus phi naught, and there is this constant phi naught also. Right? So R naught was equal to LZ squared over mu times alpha. I think that's what it was. Let me check. R naught is that, and P is looking into my notes here. Yeah. And E is square root of 1 plus E over alpha over 2 R naught. So that's your summary of whatever we have done. We first reduced our Lagrangian in terms of these coordinates in a plane, the polar coordinates, right, where r is the distance, the relative distance between the two pauses, and phi is the angle it makes with respect to some line, some reference line in the horizontal plane or in the same plane that has m1 and m2. And it's described in terms of this solution is described in terms of two constants R0 and E. And there is another additional constant phi naught, which hopefully can be chosen to be 0 with some reference line. Okay. Let's, since there is this energy in here, so let's look at that a little bit closely. So energy E is equal, so that's a total energy, kinetic energy due to the radial motion, the kinetic energy due to the angular motion, but the angular motion, because of the angular momentum conservation, I can rewrite it as 1/2 and LZ square over mu r square. And there is the potential energy, which is plus alpha over r. And it seems, no, minus alpha over r. Notice that once I replace this angular velocity in terms of the angular momentum, then this is a completely a radial a radial dependent quantity. There is only radius showing up. There is no angle showing up at all. And in that sense, if this is the kinetic energy, then this should be the potential energy. Right? So if I use the idea of conservation of angular momentum, angular momentum itself contributes or can be interpreted as part of an potential energy, and we will call this the effective potential energy. As far as the radial coordinate is concerned, as far as the radial motion is concerned, right? Even though it changes with angle, how far you're from mass m1 is pretty much governed by a potential energy, which is, if you notice, I can actually write this as, if I put an alpha in there and an alpha in here, that's your R naught. So this is nothing but 1 by 2 of, let's say, alpha times R naught over 2R squared minus alpha over R. Is that clear? Just rewriting.
Yeah, that's cool.
Okay. So that's an R dependent quantity. So let's look at where the potential energy usually describes what the energy is, right? Remember that whenever you're working with potential energy, forces in the radial direction or forces corresponding to the potential energy always shows up as a gradient, or minimization of the potential energy is what is happening. Like energy tries to be minimum, so the potential energy associated with is what is trying to be minimum. So let's see how this potential energy looks like. And if you notice, so this is your radius R, and that's your, let's say on the y-axis, I'm doing some potential energy, but not necessarily the effective one. Minus alpha R shows up as simply a 1 over R potential in the lower, in the fourth quadrant. Right? And plus 1 over R squared, these are constants, alpha, R naught, and 2 are constants, so it's 1 over R squared. So it dies out faster. So I exaggerated that thing, that it dies out faster. So that's 1 over R squared. And this is 1 over R. And it is the difference between these two quantities that decide what's the effective potential is. When R is very small, 1 over R square will dominate over R. So when R is small, this dominates. When R is very large, this dominates, because when you have a very large number, 1 over R and 1 over R square will be very small. So for large R, this second term dominates. For the small r, there is a first term dominates. So it seems like if you were to plot the effective potential energy, this time I'm doing effective potential energy with respect to r. For very small r, the first term dominates, that's this. For very large r, the second term dominates, that's this. So somewhere they have to meet, correct? So it turns out the product potential seems to be like this. And that immediately gives us a lot of insight, saying that as far as the radius is concerned, remember that this is not the complete Kepler problem. We have reduced the Kepler problem into thinking of it just as radius. Like how far is one mass away from that? Angular dependence is not being talked about. And it seems like as far as radius goes, there is a minimum. It tries to, if there was no kinetic energy involved at all, if there was no velocity coming into picture, it will like to stay right at that bottom point. But remember that it should be taken with a grain of salt when you say that velocity should be 0. You're just talking about the r dot, right? The radial velocity should be 0. It could still have angular velocity because if you want this effective potential, we have to have angular velocity. So if the radial velocity is 0, that means when for what situation do you have the radial velocity 0, but still it is moving? What is the classic scenario? So think of a motion in a plane. There is no radial velocity, but there is an angular velocity. Maybe angular should be called in terms of tangential velocity, right? That's circular motion. Okay, so this point here, when it is at the right of the center, that means it's a circular motion. So we want to analyze those situations. So let's, is that clear what I'm talking about? Ken? Any clarification needed there?
When you referred to like radial motion, it'll be like just like a spinning disk.
No. So for example, let's think of a sphere itself. So this is your coordinates, right? So in general, you could have this motion, right? In general, that's a very complicated motion there. Now think of the vector r. This is your radial component there, r hat, and phi hat is perpendicular to that. Okay. Now in general, so now this is the velocity here, right? That's your velocity, which is tangent to the orbit. That velocity has a radial component and a phi component. Correct?
I see. Yeah.
And if the radial component is not there, that means that the velocity is always in the phi direction. It is tangential. The tangent to the orbit is always in the phi direction from the center.
Oh, I see.
Right?
Which is that of a circle. Yeah.
Which is circular, right?
Yes,
so
I see.
What I'm trying to clarify here is that this whole potential energy business here, effective potential, is only in terms of radial distance. There is still angular motion there, which we have accommodated as if it was a radial component in terms of radius. Like if you increase the radius, the energy associated with it decreases, right, because of the 1/r² potential. So faster or slower as far as tangential goes has been accommodated in the first term. Does that help?
Yes, very much. Thank you so much.
So it will get clearer, I think, as we do to talk more about it. So let's, since we have an effective potential which has this form, that's your R, that's your effective potential, which is having the equation 1/2 alpha r naught over r square minus alpha over r. And total energy is equal to the kinetic energy plus potential energy. So kinetic energy plus potential energy, which is the effective potential energy, where kinetic energy is half mu r dot square. Everything in the radial direction. So if there was no kinetic energy, then the energy will likely minimum here. But let's see what is if we want to find. So immediately when you have a graph like this, you say, oh, what is this point, right? And you ask at that point, what is the minimum here? So there are two special points in that graph. So it's good to know what it is, but it is clear how to find that in using calculus. That's derivative is 0. So let's do E effective. Partial derivative with respect to R is equal to, so that's minus 2, so it's alpha R naught, R is to minus 2 minus 1, so that's R cubed. And this one will be plus alpha over R square. You would like to set that to 0. So equal to 0 implies that there is an alpha. I can multiply an R and R there, and we have R is equal to R naught. So the constant that we talked about, correct? In the solution, which was showing up in the numerator of the constant, is basically the point the effective potential energy is a minimum. And we also try to argue that at that point, if you were to have a velocity purely tangential to the orbit, then it will be actually circular motion. So if you have a circular motion for Kepler orbit, it will actually have radius r naught. And again, we will talk about this more. Okay, so that's your constant r naught. So if that is the case, what is this point? So let me call this u naught. Right? That's a special point there. Let me calculate what that u naught is. Let's go back and substitute that. Right? So u naught would be when r is r naught. That's half of alpha r naught over r naught square minus alpha over r naught. One of the r naught cancels out. So that's minus alpha over 2 times r naught. So exactly half of your potential energy. Alpha over r is the actual gravitational potential energy. It's exactly half of it. So now we know the constants u naught and r naught. And if you now go back and look at your eccentricity, or E that I defined, I haven't yet called it the eccentricity. If you notice this expression here, that is this alpha over 2 r naught showing up. But notice u naught is minus of that. So if I were to write it in terms of minus u naught, I'll have 1 minus E over u naught. So that's another way of noticing that. So our solution has two constants, r naught and E. R naught is basically the point at which the effective potential energy goes to is a minimum, and the constant E, which we will call eccentricity very soon, is basically the ratio of energy to the minimum of the effective potential energy. Okay, so that's all good. But we also know that if you have a potential energy, if you provide kinetic energy, the energy is slightly larger, right? So energy has to be K plus U. Since K is always positive, kinetic energy is always positive, and U effective, if that is a minimum, energy has to be larger than that. So this is the minimum quantity you can get for energy. When K is equal to 0, when the object really comes to a rest, in what sense is it rest? Remember, again, angular motion is allowed. Right? It comes to a rest radially. That means there is no change in the radius. That's perfectly fine, and that is basically the circle. Circle is the smallest you can get. That's the closest you can get in a sense. So if kinetic energy is 0, energy is U effective. So what we are concluding is that energy has to be greater than, so the total energy of the system has to be greater than U naught, which is a negative quantity. U naught, we saw that this is 0, negative, right? So that's 0. So that's minus alpha over 2 r naught. So energy has to be greater. And if you have slightly larger, then you can be somewhere here. So that means as you increase energy, the particle can start moving around here, exactly like analyze it as if it was in a valley, in a real valley, in a real gravitational valley, where if you go slightly higher, the charge or the particle can move around here. If you increase the energy, it can go farther. Increase it further, it can go very far. But if you increase greater than zero, then on the right hand side, it can go all the way to infinity, right? And it might not even come back. So let's talk about that. So there are four solutions possible apparently. So since E has to be greater than zero, now we have few situations here. So again, the diagram. So that's your R, that's your zero, that's your effective potential energy being drawn, and that's your R naught, and that's U naught. Energy has to be greater than U naught. So the first scenario is that energy is down here. So if energy is here, then this is E is equal to, so the total energy will be zero in this case. Right? Kinetic energy, no, total energy will be U naught, sorry. So that total energy will be exactly E is equal to U naught. In this, so that, and we will see that this will correspond to a circle. Like the orbit will be a circle. I haven't shown you that properly, but let's start. There is another regime where the energy could be down here. So anywhere in that region, energy is greater than U naught, which is a negative quantity, but it is less than zero. So the energy, total energy will be zero if it is here. And in that case, you get an ellipse. And few characteristics are clear. If you again go by the analogy with the valley, motion in a valley, if you have this much energy, it cannot go beyond that. So if you have a ball in this valley, it can start from here. Maximum it can go is here when the kinetic energy becomes zero there. All the energy is in the potential energy form. When it goes down, there is motion there and it can come back. Right? So that's your elliptic motion. That is the point here when energy is exactly equal to zero. Like that is this point here. When energy is exactly equal to zero. And on above that, energy is greater than zero. So let's say this is zero and energy is greater than zero. And if it is greater than zero, this is a hyperbola. And exactly when E is equal to zero, you think of the conic section that I told you last time, and this is a parabola. At the boundary between hyperbola and ellipse.
Dr. Shujash.
Yes, please.
So, is it true that like with both hyperbola and parabolas, the object wouldn't come back?
Exactly, it wouldn't come back. So for example, if you start from here, right? So that's your total energy. It will start moving this way. Right? It will go there and it will go all the way to infinity. Never come back. That's a comet. Not a comet. Certain comets. There are these two types of comets. Comets that come back once in a long time duration. So most of the comets that we know about, they start from here and then they go very far and then they come back. So almost once in a lifetime kind. But there are comets which will just come once. That's it. And that's the end of story. And then they go all the way to infinity or they escape from our planetary system. That's what it means. And that is very fine if you start from here, right? Right, exactly at zero. That's a parabolic curve which again doesn't come back. It will go right until the edge of our universe, and then we get to be not sure whether it's come back or not. But that's pretty much the same as hyperbole. Yeah, good point. Yes. Yeah. Clear?
Yes, yes, thank you.
And these points, so now that we have talked about it doesn't come back, right? So these points here, there the kinetic energy is zero, right? So if the kinetic energy is zero, do they come to a stop there? Like, it's a tricky question. I tried to convey that before. At this point, what's the velocity of the object? Remember again that these are angular velocities still there. They don't come to a stop. So how do you want to see that? So that is, sorry, let me try to draw this. This is finding it difficult to draw this, so let me have some reference lines. These are two circles, right? Now notice what these two circles mean is that this is the maximum point it can go. That's a minimum point, right? So these two points tell you that there is a maximum radius and a minimum radius. That's a maximum radius, that's a minimum radius. But the motion can be there in between. So how typically it looks like is the following. So it goes here and then touches the maximum and then comes back here. And let me see. Okay. It helps. Yeah, maybe. Yeah, that's a reasonable one, right? Yeah. So, now notice at this point, that's the maximum value it has reached. It is not at rest, it is still moving, correct? In the tangential direction. So these are not called equilibrium points, instead they are called turning points. This point here, that's a maximum, and that is actually the turning point. This corresponds to that. And this point here corresponds to this. Is that clear?
Yes, yes.
So these are called turning points. So we would like to find the turning points, right? Let me see. First let's talk about the r equal to 0. Let's talk about the circular motion now that we have all the constants. Oh yeah, I have to talk about phi naught. Right? Yeah, so let's choose. So we have, let's choose, like choose, right? Choose phi naught is equal to 0. Right? That's basically choosing one direction in the plane as a reference line. And then we have the radius as a function of angle to be r0 over 1 plus e times cosine of phi. Okay. And then let's ask what happens to this orbit. It is clear that when phi is equal to 0, it is actually the denominator is the maximum, and when phi is equal to pi, it is actually the denominator is a minimum, which means it's the opposite, right? So our minimum would be equal to r0 over 1 plus e, and our max would be equal to r0 over 1 minus e. Correct? And you would say that, oh, motion should be inside this, so that is the maximum. And actually, I want to correct something. This is a wrong statement here, because I was trying to give an analogy. I was trying to explain what the turning points are, but here I seem to convey that this is a solution for this problem. But this is not a solution for this problem, because a Kepler problem will come back to that same point. Right? In one orbit, it will come back to that same point. Because phi plus 2 pi, if you need notice, phi plus 2 pi will exactly be the same. Cosine of phi plus 2 pi is the same. So it will repeat. Radius will start repeating it again and again, which is not conveyed in this point. This is a precision problem. It is possible under spherical symmetry, but not for 1 over r problem, not for Kepler. If you have a perturbation and so on, it's possible. But I was trying to illustrate the fact that these are actually turning points and not necessarily a point where it comes to a rest. Okay, is that clear? So this is not a solution. So this is following is not a Kepler solution.
The solution would just be one orbit.
Yeah, there will be only one orbit. But in general, I can expect something to be like this. That's all I was trying to describe that. And this tries to describe clearly that there is a radial minimum, radial maximum, and the particle is always within this regime, inside this. Correct?
Okay. Yeah. So I have a question real quick. So there, it looks like there is like a limit between how like thick that donut can be, right?
Tell that again. I didn't hear you.
Yeah. So it looks like there's like a limit of how thick that can be, right? Like how thick the donut, the shaded area can be, like.
Oh yes, exactly. Yeah, and that will be your eccentricity.
I see. Okay.
So for example, so this is not allowed. So let me remove this. Having seen that picture, the idea is that there is a minimum and a maximum, right? So you have this line here. So if I choose my coordinate system here, there is a minimum and there is a maximum, right? What's the maximum? That's a maximum. That's a minimum.
Yes.
So when it is pi, it is a maximum, and that, like, how much you stretch your ellipse decides your eccentricity.
I see.
The ratio between this minimum and maximum. So let's define that more precisely now. Okay. With me till now?
Yes, thank you.
Okay, so let's actually, before we go to the ellipse, let's so now that we have four situations, right? Let's analyze this one after the other. We won't analyze everything because hyperbola, even though it is completely different, it follows lots of the characteristics of ellipse. So I will leave that, just keeping time in. Actually, I would say that this is very interesting that hyperbola should be analyzed separately, but keeping time in constraint, we will do mostly ellipse. Okay, so we will do the ellipse, and then a similar thing I would say is recommended for a hyperbola. So how about this? So this will be a quiz. So whatever I do today, repeat it for hyperbola. So the quiz problem is repeat whatever I do for ellipse for the hyperbola case, which is relatively long quiz, but keep it more as your own, for your own self. Like submit just a few lines, or and I should say that this whole content, I have used Landau and Lifshitz for this, so look it up. So it's a reference material for the course, and it's just one chapter, but it is very well described. That's the best description I've seen for this, and most of the textbooks follow the description of Landau and Lifshitz, but since it's original, it's kind of very nicely conveyed. Okay, so let's basically, I'll talk for a few minutes for circle, and then we'll get into our ellipse. Okay, clear?
Yes, thank you.
Okay. So let's so we have energy. So let's first do circle, right? Energy is equal to minus, or energy is equal to U naught. Right, so that's circle. So what is that? Mean energy is equal to U naught. So remember, energy is kinetic energy of mu r dot square plus U effective but if E is equal to U naught, that's a minimum possibility for this. So this implies that R dot is equal to 0. Is that clear? For a circle. Confining ourselves to this.
Yes. Yeah, that's clear.
If that's there, then let's go back to our R naught is, so R is equal to R naught then. And E is equal to, so that's your solution. And E is equal to eccentricity is E is equal to U naught. Remember, that's 1 plus E over alpha over 2 R naught, which is equal to 1 minus E over U naught. If E is equal to U naught, this is exactly equal to 0. So this constant, we will start calling it not yet eccentricity. This constant E is equal to 0 for the case of a circle. And this is the equation of the orbit. That's the solution, right? Orbit. Trivial, right? Because E is equal to 0, R becomes R naught in the solution. And that's your circular motion. Because you still have mu R dot phi dot square is equal to LZ. So you still have circular motion. In all this orbits, circular motion is understood because angle represents time. Okay, so that's your circular motion. Now let's go to the next situation where U naught energy is less than 0 and greater than U naught. Right? That means energy is, total energy is always negative. Right? That's usually called a what's the word for this? One is called an open no. What's the word? One are called scattering states and one are called confined systems. Yeah. This is an example. Whenever energy is less than 0, total energy is less than 0, it means that it is confined. If it is greater than 0, that means it's a free particle. That means potential energy is not dominating. It is a kinetic energy that is dominating. Okay? So in this case, kinetic energy is less than magnitude of the potential. So it cannot escape the potential, so it will be confined. And this will be our ellipse situation, but we're going to analyze that. So that's the case we are considering. So let's again go to our total energy. So total energy is equal to half mu r dot square plus U effective is alpha r naught over 2r square minus alpha over r, right? And clearly we said that if r dot was equal to 0, then they are the turning points. So let me find those points where r dot is equal to 0. So to find the turning points, what I do is I set r dot is equal to 0 in that equation. So I get E is equal to alpha. So which are the points of at what r does that happen? So that's alpha r naught over 2r square minus alpha r. Right. So that should be a quadratic equation, I suppose, and we should see two solutions. So let's see. So let me write this as, how do I do this? Notice that energy is negative here. So let me write this as negative of a positive quantity, correct? And that's equal to, let me do this as alpha over 2r naught, and that's r naught over r the whole square minus alpha over r naught, and that is r naught over r. So this is a quadratic equation in r naught over r, right? And can I do something? Yeah. So if I were to divide this by u naught, should I do that? Wondering. How? What's the right? Yeah, so let me do, this is minus energy over magnitude of u naught. U naught, remember, is alpha over 2r naught. So that's r naught over r whole square. And this is minus 2 r naught over r. So that gives me a quadratic equation in r naught over r. Probably. So let me explicitly do that. Is equal to 0. So my two solutions are r naught over r is equal to naught over r. So these are the turning points, right? Not arbitrary r. Minus b, that is divided by 2. 2 cancels out, plus or minus r naught over r square minus 4se, right? 4e over u naught. No, 481, right? Sorry. Oh, what am I doing? Right. Yeah. So this is a variable, right? So this is minus b, so it's 1, correct? So this is just 1 plus or minus square root of 1 minus 4 times 4 has been taken out. So that's e over. Correct. And notice this is actually the e because E is negative, U naught is also negative, so I can release the magnitude. As far as I'm in the ellipse case, right? So this is actually the negative quantity in this.
Dr. Jajesh.
Yes.
What equation exactly is that? Did you use is that like the quadratic theorem or?
Yes, yes. So this is your what is this? X squared minus 2x 2b, right? So 2b uh, x squared plus bx plus c is equal to 0. Ax squared plus bx plus c is equal to 0. X is equal to minus b plus or minus b squared. Correct? I use that.
Yeah, I see.
So here A is 1, B is 1, C is E over U naught. Correct?
So B isn't -2 in that sense?
B is negative 2, right? So in our case, B is 2.
I see. I'm sorry.
And C is so on. So in our case, I think I said it wrong earlier. So I said B is equal to 1. So B is negative 2. So this will be plus 2. So negative of negative 2 plus or minus 4 minus 4 AC if you want. Divided by 2A. Right?
I see.
So the 4's all cancel out. So 1 plus or minus 1 minus AC over A. A is 1 for us and C is given to you. Is that clear?
Yes. Sorry, I didn't see that before.
Which is actually the same as, so be careful here that this is 1. If I were to not write the magnitude, energy is negative, and this is also magnitude is alpha over R naught. So that's the same as 1 minus, since energy is negative, I actually give that negative sign to E, so that's plus E over alpha over 2 R naught. There's few negative signs coming in, so it's confusing there, but that's exactly equal to 1 plus or minus E. Agreed?
Yes.
And that's your turning points. So if you were to compare this now with your equation, let's say, so I have this R is equal to R naught over 1 plus E cosine phi. And and if you were to compare with the turning points, so let's say R turning points, T means turning points, that's R naught over 1 plus or minus E. R is 1 plus or minus E. And it seems to be happening at phi equal to 0 and phi equal to pi. That seems to suggest that. And that leads us to realize that this is like this, right? So this is it. So there is a reference line. So at phi equal to 0, that's the minimum. So what you want to choose is that, so this is the radius R, so that's one of the points. And so this is phi equal to 0. That's phi equal to pi. And that's your R minimum. So let me define R minimum. R minimum will be R naught over 1 plus E, when pi is equal to 0. And R max is equal to R naught over 1 minus E when phi is equal to pi. So that's our minimum, and then this is our max. So some exposure is coming in. So that's your reference line. But This is your origin though. So that's your origin. This is not the origin, right? This is R is being measured from here. So that's your R. That's your R. Is that clear?
Yes.
So it's kind of usually it might be more natural to put it here, but the way we made our choices, our origin is on the second foci. And of course, this is angle phi. That's your angle phi. Let's define, like, since we are going to expect that this is actually going to become your ellipse. So this is in an ellipse. This is called the major axis, and that's 2 times the major axis. So it is clear that 2 times A is equal. So this is your minimum distance. That's your maximum distance. That's your minimum plus maximum. So that gives me a way of measuring my major axis, right? I will be able to write it in terms of R naught and E. So that's equal to 2 times A is equal to our minimum is R naught over 1 plus E. This is 1 minus E. Put this together. That's R naught, 1 minus E and 1 plus E. The E cancels out. So this is 2 times R naught over 1 minus E squared. That's 2 times A. So we get a relation for A is R naught over 1 minus E squared. So semi-major semi-major axis is exactly given in terms of R naught and E square as given by that expression. Okay. Let's define one more thing. That's the semi-major and minor. So I'll define focal length to be the difference between your semi-major axis and our minimum. So let me, so that there's a focal point here, right? So let me define this length to be the focal length. So what is the focal length equal to? Oops. So the focal length is equal to A minus our minimum. So that's A minus R naught, R naught over 1 minus E squared minus of our minimum, which was R naught over 1 plus E, which is equal to, I multiply by 1 minus E on both sides. That's R naught minus R naught 1 minus E divided by 1 minus E squared. So that makes it R naught times E over 1 minus E squared, and that's your focal length in terms of your constants R naught and E, which is, of course, if you were to use this in here, this is also A times E, or let's say E times A. So focal length, since if it is always less than A, so E is always less than 1 in this case, which is already there because our energy is less than 0. Eccentricity is always less than 1. Right? Remember, recall here. Recall that eccentricity is equal to 1 So it is 1 plus E over alpha over R naught to R naught, and energy is greater than minus U naught, less than 0. So this is minus, so E is always less than 1, right? So that implies that E is always less than 1 and greater than 0. Is that clear? Any confusions there?
The A minus R min, you're saying that that's the focal point, right?
Tell it again.
The A minus the R min. Oh, okay. I didn't see that. Yeah, never mind.
Yeah, I think the things were switched or moved a little bit. Yeah, now it's better, I guess. Yeah. Okay.
Yeah. So I see that the focal point and the eccentricity is like really closely linked.
What's the question?
The question is like how do I'm sorry, I'm trying to figure out how to say it.
Yeah, sure.
So there, okay, here's a good question. So similar to like the Lagrangian multipliers and stuff, is there a tendency for these orbits to move like out of the way? Does that make sense? Like to change? Like, does the R?
Learning is that's the good question. But these are equations that's being put forward to us, right? It's not that we are constructing it. If alpha, so if potential energy is visible here, if potential energy is confined to minus alpha over R, right? That's your gravitational potential energy. You don't have much choice. If that was the only case, and if we are doing two-body problem, okay?
Mm-hmm.
A very limited scenario that we have a sun and Earth. That's all. There is nothing else. No Jupiter, no Mars at all. Then it's a simple ellipse. That's it. If you move a little outside, you have to provide energy. You fix your energy, you fix your angular momentum. That's it. You will do that. You will do this elliptic orbit forever.
I see.
So it's a very solid solution, kind of. Like if
Yeah.
you have energy equal to negative U naught, then you will be a circular orbit forever, unless you're perturbed.
Yeah, I was thinking of it in the terms of tension, instead of tension being gravity.
If it was a tension, then it's a completely different potential, right? Then it's a different game altogether. For that matter, even if it was R square, right? Even if it was R square, which we will talk about in the next class. If it is R square, then it's different. Then suddenly all this precision begins.
I see.
Okay, but alpha over 1 over R is very special. It is remarkable that you are in such a scenario.
So I mean, if we have time, could I ask a couple more questions?
Yeah, please.
Okay, so wouldn't looking at it kind of retrospectively, where it is just the sun and the Earth.
Yes.
If we were to launch off of Earth with a rocket, wouldn't that add energy to the orbit just a little bit?
That's correct, because it's a three-body problem. Yes, very much. And the point is that tiny bit. See, for that matter, let us say you are talking about a spaceship which is really tiny, right? But let's say we include Jupiter. Okay, let's say that we do a three-body problem and we want to introduce what is the perturbation on Earth's orbit due to the presence of Jupiter, which is a major perturbation. But if you try to do it, it turns out that the effect of Jupiter is really small. So it does change this orbit, but it's small. Like it will perturb it a little, so it's jitter a little here, and mainly this will start precessing. And if it is all spherical, this will start precessing. So the effect is mostly an ellipse, dominantly ellipse, but it changes. How can it change? It can start precessing, it can start radially. It's like, for example, it can start wobble, right? It can, instead of going this orbit like this, it can do this. Right? It will go a little away, come back closer. So those are all the perturbations possible. You see what I'm saying?
Yes.
But mostly
Yeah.
it will stay as an ellipse.
Okay. Okay. Thank you. And my next question.
Yeah, go ahead. Next question.
Yeah. So with the Moon and Earth system, it's the central mass that orbits around. Like that's what would be the.
That's correct. That is correct. And
focal point. Okay.
You're right. You're right that Moon's presence disturbs Earth's orbit, and that is where this system comes in. Right? It actually does this. It will go a little farther, closer, but a very small amount. Yeah, it does do that.
So when we put satellites in Earth's orbit, that also does it, but in a small amount?
That also does it, but probably very minor. Because remember that Earth's mass is 10 raised to 24.
Right.
And what comes into picture is that Earth's mass is 10 raised to 24. Let me raise this part. So if you say the mass of Moon, so Moon over Earth, right? The mass ratio is, this is 10 raised to 22, and this is 10 raised to 24. Even if you keep one digit, it is 7 times 10 raised to 2 and 6 times. So that's 1 in 100. So whatever effect is going to happen, it's going to be 1 in 100. If this radius is 1, then 0.01. But what about a satellite and Earth? Satellite over Earth, that's about 1 in a 10 raised to 24. Probably doesn't even budge it. Even if you had to put 1 million satellites out there, probably nothing is going to happen.
Okay.
You see, because million is 10 raised to 6, right? Still you're in the 18th digit after the significant one. Right?
Yes. So, I guess I was just thinking of it in that very minute amount, specifically because of like satellites and GPS. And I was just curious if like the satellites and GPS would be affected by even more satellites being launched into.
It will affect it, but in the 18th decimal.
Yeah, right. Okay.
In the 18th decimal, yes, it will get affected if there are 1 million satellites out there, which is kind of, we are reaching that stage where there are 1 million satellites. But yeah, if there are 1 million satellites, the 18th decimal will be affected. But GPS doesn't depend on the 18th decimal. GPS depends on pretty much 3rd or 4th decimal.
Yeah, we can't geologically position a centimeter, right? So yeah.
Exactly.
Okay, cool.
It is pretty much like saying, if I were to jump on Earth, how much does Earth get affected? It does get affected. It's true. Earth gets affected. Earth jumps back a little bit, but it's in the 20th decimal.
Right.
So, yeah, good point. Yeah. And I think in this context, I should say, remember that I had talked about inverted pendulum?
Yes.
And I had said that, if you were to oscillate that pendulum, there is a stability that comes in. Discussion? Now, that discussion actually originated in this. So when we talk about Moon here, oscillating here like this, the first time it was asked that if Moon were to oscillate like that, is there an instability that can come in due to that? And the equation that's associated with that is called the Matthew equation. So it's a good question to ask that due to this up and down motion of Moon from the ellipse orbit, even if it is tiny bit, is it possible that it can get unstable? And that is what is discussed in that, and that's simplified into a pendulum scenario. That's what we talk about.
Hmm.
Else?
Yes, yes, thank you.
That's all good. So now we have this equation. So let's do one more thing, and let's usually we see equation of an ellipse in rectangular coordinates, right? X and Y, right? So let's try to see how that shows up. And before that, it is good to also point out, so get rid of these things. One point is clear that what is R naught? Remember your equation. So yeah, so if I were to actually go up here a little, that's my solution here. When does R equal to R naught? And it's clear that when the denominator becomes 1, that's phi equal to pi by 2. So it's good to know that R is equal to R naught when phi is equal to pi by 2, which is down here. Is that clear? So that's your R naught. It's good to have that reference on that. And I think I mentioned it before also in the last class also. Okay?
And that's symmetric?
That's what?
Symmetric on the other side as well, right?
At the bottom side, you mean?
Yes, yes.
Yes, because phi equal to pi by 2 and phi equal to 3 pi by 2 also this is equal.
Understood. Yeah, thank you.
So that's also good point. That is if this ellipse is very much exaggerated, that means its eccentricity is very large. For example, Pluto's orbit or Neptune's orbit. But for Earth, this is really close by. This is close by in the sense this is a difference of 1 day. So it's very tiny. Okay,
I suppose
so
that's why.
Other again?
Oh, sorry. I was just gonna say. I suppose that's why our weather doesn't change much, right? Because we have such a circular orbit. Like we have winter and summer, but not to an extreme degree.
Okay, so that leads to another question for you. Okay, whatever you said is actually wrong. So here is the point. Okay, so you said just now that from what you said just now, this will be summer, this will be winter, correct?
Yeah.
I think I moved it again. Right, that will be summer, that will be winter.
Yes.
Agree? So here is a question for you. On Earth, when it is summer in Norway, it is winter in Australia. How do you go with that?
Oh yeah, yeah, I see.
Okay.
So
summer and winter has nothing to do with elliptical orbit.
Right.
Okay. So what does summer and winter have to do with?
The tilt.
Huh?
Probably the tilt and precession of the Earth.
Exactly.
Right?
It has everything to do with tilt. Just because Earth is tilted, because it's tilt here, and it is the rays of light coming and falling at an angle, that's everything. Very, I mean, unless you think about it closely, it doesn't strike at all. It's very tempting to think that, oh, it's summer and winter because it's closer and farther, right? It's very tempting, but once you give it a small thought on it, it comes, oh, yeah, of course not.
Well, surely that would have an effect, though, right?
Yeah, it has an effect, and that is everything. So, for example, this tilt is what gives you. So, this one is winter in Norway, right? Because if that's North Pole, that's winter in Norway because it's farther, and here it's closer. So, this is summer in Australia. Okay, just because of the tilt.
Right. Okay.
Okay, remarkable. Yeah.
That's awesome.
Okay, if you allow me, I'll take 5 more minutes or 10 more minutes maybe.
Yes. Yeah. Take as much time as you want.
So let's go back to our equation. We have R is equal to R naught 1 plus E cosine phi, right? Let me write that as R plus E times R cosine phi. I multiply this out. That's equal to R naught. Agreed? These are in polar coordinates. So let me write my x as R cosine phi and y as R sine phi, which means x squared plus y squared is equal to R squared. So let me use that to replace these quantities. So this is x squared plus y squared square root plus e times r times cosine phi is x, and that's equal to r naught. So let me get rid of this radical, take this to the right side. So this is x squared plus y squared is equal to r naught minus e times x squared, which is the same as r naught squared plus e squared x squared minus 2 times r naught times e times x. Let me bring all that to the left and see how we can process this. So that's 1 minus e squared times x squared. These two taken care of. And then there is plus 2 times r naught e times x. That's this taken care of. And then I have plus y squared. Okay. Let me go to the other board so I'll have more space actually. It's only a few steps, but and then I'll stop. Then that gives you the equation of ellipse and rectangular coordinates. So let me rewrite that. So you have 1 minus e squared times x squared, rewriting that whole expression. So it's 2 times r naught e times x plus y squared is equal to r naught squared. Let me make this a total what do you say? Total as whole square. So this is squared, so that's your x, and plus 2 times. I want to have this, so it is 1 minus e squared times x. So I have actually multiplied e times r naught over 1 minus e squared. So that's the same as this. These two terms are the same. I just multiplied and divided it out. And then I can add plus e times r naught over 1 minus e squared, the whole square. So I've done addition, so I have to subtract that out, r naught. So do the same thing on the other side also. Okay. Okay. that's the same as. Actually, put this all together here. So that's 1 minus e squared times x plus e times r naught over 1 minus e squared, the whole square, plus y squared is equal to this quantity in here. So this time I write this as r naught square plus e square r naught square over 1 minus e square, which is the same as if I were to put this on the other side, the e square cancels out. So this is the same as r naught square over 1 minus e square. And if you notice, that has something to do with a, right? So we'll come to that. So let me pull a 1 minus e square out. So that becomes 1 minus e square and then divide it out. So this becomes x minus e times r naught over 1 minus e square, the whole square. Are still in the board space? Yes. So that will be 1 minus e squared out. That can be written as, when I divide it out, that's y over 1 minus e squared, square root, the whole square, and that's equal to, this is r naught square, r naught over 1 minus e square, because I'm dividing out by 1 minus e square, the whole square. Okay, that's, I think, what I wanted, but can we identify stuff here? R naught over 1 minus e is a, right? So that's one thing. And we also had the focal point, right? So remember that a was equal to r naught over 1 minus e squared. And your focal length, where was focal length? So focal length was equal to r naught e over 1 minus e squared. So what I'm seeing here is that this is x minus f, the whole square, plus, that is y over 1 minus e square. So let me write this as y square over 1 minus e square. That's equal to, this is a, so that's a square. Divide it out. So this is x minus f, the whole square, over a square plus y square over 1 minus e square times a square is equal to 1. Write this as x minus f, the whole square, over a square plus y square over b square is equal to 1. So this is an ellipse centered at f comma 0. Center of the ellipse is at f at 0. Major axis is a. This is a, which is equal to r naught over 1 minus e square. And minor axis is b, which is 1 minus e square times a square, right? B square is, and f itself is equal to, given in terms of those quantities. So that's clearly, that has all the information in it in principle. And one can go back and now do this for energy E is equal to 0. You get parabolic solutions. And then you do this for hyperbola, which most of what we did here kind of corresponds to that, but there everything is related to hyperbola, properties of a hyperbola. Helps?
Yes. So couldn't you just like for instance with a circle, E becomes zero, right? So, and then you get the equation of the circle from that.
That's correct.
Could you do the same with the parabola and hyperbola? Like you
Yeah,
wouldn't need to
parabola and hyperbola, what you do is, so you start from the case where capital E is equal to 0 will be parabola. Right, so eccentricity becomes 1.
And then you can just refer to this equation again, right? Like
yes, so then you will get a parabola equation. So that's one of the things that typically I do when we have more time, that you start from your conic section equation, set E is equal to 1, the small e eccentricity is equal to 1, and you can show that that's a parabola equation in x and y coordinates.
I see.
So kind of it comes in few steps, but yeah, it doesn't take too long.
Well, thank you so much.
Yeah. Yeah, it's interesting, but I think I'll not go through that. If you want, I can go through it, and we will have to sacrifice something.
No, I don't think so. I'm going to attempt to do it myself.
Yeah.
And then
Yeah, I think you have all the tools here. Now you can actually explore.
Right. Yeah, I was hoping like I could, code some of this on MATLAB and see some plots and stuff from it. That's what I wanted to do. So.
Good. Yeah.
But yeah, thank you so much, Dr.
Yeah. Okay, Ken. Yeah. Have a nice day. Bye.
All right. You too. Goodbye.